In this video we're going to cover heat transfer. That's actually kind of a redundant term. Heat is thermal energy transfer. So we shouldn't even have to use the word heat transfer. We should just be able to say thermal energy transfer or heat. The thermal energy due to heating can be transferred in three different ways. One way is you can have two different objects with different temperatures, or even a single object that has different temperatures at different parts of it that is in direct contact, and the atoms bang directly from objects of one to the atoms of the other object and transfer that energy. A lot of this is usually done by electron transfer, and so good electrical conductors are usually what are called good thermal conductors. This process is known as conduction, and we often say this is thermal conductivity. So conduction occurs when the atoms of a system directly interact, i.e. the systems are in thermal contact. The other two ways are convection, which is usually done when a heated object transfers energy to the molecular motions of a gas, and then that gas carries the energy away and then transfers that energy to some other object. And the last one is by radiation. An object can get so excited, and because there are charges inside of it, those charges are accelerating, and the accelerating charges inside will then transfer or create what are called electromagnetic waves. Now, we haven't studied electromagnetic waves yet. We'll study them later in the course. But this is what we've all noticed. When you heat an object at a high temperature, it has a color. In addition to having a color, even though you don't touch it, you can feel the warmth. Something is radiating outward to you. And it radiates even if you suck the gas out. There's something that can come out just like the light, and that's electromagnetic radiation. So the three ways: conduction, that's direct touching; convection, the object touches usually a gas, and there's a general molecular motion; or by radiation. In the first one, conduction, I have a temperature at TH that's at some high temperature, and another part is T cold. These could be different objects, or they could just be different part of this bar. And this bar on one end, right here, because it's touching that object, maybe that's a stove, it's at TH, and at the other place it's TC. And in between, energy is flowing through that. These molecules are moving faster. They bang into the slower moving molecules. The slower molecules pick up speed. They bang around, and there is a net flow of motion of the molecules as the molecules go this direction. There is a length. The further the distance between these two things, that is, the more collisions these atoms have to make to eventually transfer that energy down here, the slower the rate at which it occurs. That's because they have a finite speed. Also, the more atoms that can get involved, the faster this can occur. Well, the number of atoms that can get involved depends upon this area, how many that can bang in. So this is the cross-sectional area. So I would expect some things to be. I would expect that the heat that can be passed per time should depend upon the temperature difference. The greater the temperature difference, the more energy per molecule up here, the less down here, the more it's going to be able to transfer energy to these slower moving ones. I would expect it to depend upon this cross-sectional area. If only two atoms could hit, that'd be a lot less efficient in transferring it per time than if 10 to the 20th can hit. So I'd expect it to depend upon the area. And like I said, I would expect it to be inversely dependent on this distance, because it's going to take time for it to travel at some mean speed all the way over here. So I would expect this to depend inversely with L. And in fact, that's exactly what we find. So we can write this as an equation that goes something like this. The heat transferred per time is equal to some constant times the change in temperature divided by the change in length times the area. Now, in calculus classes, we can talk about what's called a gradient. That is, it's not just the change in temperature, it's temperature per length. This is the cross-sectional area, and this proportionality constant has a name. It's called the substance's thermal conductivity. Some materials have particles inside that can move very quickly. And because they can move quickly, they can easily move a lot of energy very fast. And so this K is very large. A lot of energy will get transferred in a very small amount of time. Remember, this is time, and this is heat. So this is heat flow rate, and it's in joules per second. So large Ks are said to be good thermal conductors. Examples, these are most metals. They have free electrons, and the free electrons can transfer energy. Now, there are also things that have small Ks. And when they have small Ks, you could say they're poor thermal conductors. But what we usually say is that they are thermal insulators. And this is what you want to put around your house. This is what you want to put around thermos if you do not want energy to be transferred. You want to keep the energy at one place. Now, working with small Ks is a pain, so instead, most manufacturers who make insulating materials prefer to work with what are called R values. And an R value is just the inverse of the thermal conductivity. So it's 1 over K. So a high R value means a small K means that it's a good insulator, it's a poor conductor. So when you talk about insulation for your attic or such, they give you the R value. They're giving you the 1 over the K. The fact it does not like to conduct. A high R value means a very small conductivity value. Now let's look at convection. Convection questions are generally not going to give you a formula and have you do calculations. What they are saying is that the thermal energy is transferred by mass movement, often in the case of a gas molecule. So, for instance, let's take a thermos. In a thermos, this is your outer surface. And this is your inner surface. We don't want these two to touch by conductivity, so we don't. But if there's air in here, gas molecules, these molecules will get heated up, excited by the surface, migrate over, hit, and bang into atoms on this surface, thereby transferring energy. That process of the gas molecule movement is called convection. So in a thermos, what they do is they evacuate this. So they don't let the two touch, so there's not conduction. Then they remove the air in here, creating a vacuum, which enables them to reduce the convection. Similar thing can happen in storm windows. Either you can put two plates with a glass that's trapped so it can't move very well, so that it has slow movement, or you evacuate. The problem with evacuating glass between here is if the glass is really large, it creates a tremendous force and it will implode. So the glass won't handle it. But for a thermos, you got a metal container on one side and a much smaller glass section on the inside. This helps the process of being able to handle a vacuum, at least a small vacuum in here. The last process, radiation. Well, in the radiation, what we get is we get a heated object, and that heated object gives off energy in the form of electromagnetic radiation, and the formula for that is the amount of energy lost per time. So if you prefer, sometimes we simply say power is equal to the emissivity times the Boltzmann constant times the area, this is the surface area, times the temperature to the fourth power. The emissivity can range from 1 for a perfect absorber to 0 for a perfect reflector. So if you want to make something like you want to make a good stove, black is perfect. It only absorbs energy, but when it absorbs energy, it equally likes to re-radiate it out as electromagnetic radiation. A perfect emissivity actually isn't a black stove because black still does reflect. The best is what's called a black body. And a black body is a body that's not necessarily painted black at all. It's a cavity where you cut a hole, and when you look in that hole will look black because any radiation light that goes into that hole will bounce around, bound, and like a fish trap, it won't be able to get back out. So the inside hole of a cave or such is the idea of a true black body, not just a black object on the outside. As you raise the temperature, if you double the temperature, you get 16 times as much energy. What else do you want? You want as many sides radiating with as much area as possible. So the bigger the area of your stove, the more power it can put out. The higher the temperature of your stove for your heater, the more power it can put out. This constant, named after Dr. Stefan and Boltzmann, is simply a proportionality constant that has to do with the fundamental nature of the universe. And the E, like I said, for a lot of heated objects is just taken to be 1. The sun itself is basically a radiator. It has an area, it has a temperature, and it has a power. And because we can measure the power that it gives off, we can determine the temperature of the surface of the sun without ever landing on it. Did you ever wonder how they know the sun's temperature when we don't actually land on the sun? This is how. All right. This covers the remaining materials in Chapter 14 of Giancoli, or it covers the section on heat transfer if you're in a different book.